Hello, and thanks a lot for joining to this talk on our paper Everything Old is New Again, Binary Security of WebAssembly. My name is Daniel Lehmann, and I'm going to present this joint work with Johannes from Bundeswehr University Munich and Michael Pradel and me from University of Stuttgart. Before we go into WebAssembly security, I just want to briefly introduce what WebAssembly is about. So WebAssembly is a relatively new bytecode, so a binary format as you can see here, that is fast, low-level and portable, and is originally intended to be executed on the client side in web browsers as a complement to JavaScript, for example, for compute-heavy applications like video codecs or compression or game engines. By now, WebAssembly has gained a lot of momentum, so it's supported by over 90% of all global browser installations, and more recently also on Node.js for server-side applications and even in standalone virtual machines. As a bytecode, you typically wouldn't want to write a WebAssembly program by hand, but instead you compile it from often systems-level languages like C, C++, Rust, Go, and also many others. Now, given that a lot of legacy code is written in those memory-unsafe languages, the question of security comes up. So what happens if a memory vulnerability in a source program is compiled to a WebAssembly binary, and then at runtime an attacker supplies malicious inputs to that vulnerable binary? For native architectures, a decade-long cat-and-mouse game have resulted in a plethora of very good mitigations against such runtime attacks. So that starts very early from virtual memory provided by operating systems to compiler-inserted defenses like stack canaries, or more recently, elaborate defenses like control flow integrity, for example. Now the question is, how many of those mitigations are available and employed for WebAssembly binaries? And if they are, how effective are they in preventing runtime attacks? So does it make a WebAssembly binary always more secure than a native binary, for example? Or is it in some cases even less so? Proponents of WebAssembly have made strong claims about its binary security. So a WebAssembly design document states, for example, that data execution prevention and stack smashing protection, so stack canaries, are not necessary for WebAssembly programs. And we wonder, is that actually true? And another document, the original PLDI paper, says, at worst, a WebAssembly program could make a mess of its own data. And we wonder, what are the consequences of that? We aim to answer these questions, and for that our paper contributes first an in-depth security analysis of WebAssembly, including one of its major components called linear memory. Second, we provide a library of attack primitives, and those primitives can be freely combined to perform an exploit. Third, we give 3 different proof-of-concept exploits on 3 different WebAssembly platforms to show that they are feasible in practice. And finally, to quantitatively assess the risk, we do some measurements on real-world binaries. For time reasons, in this talk we can cover only so much detail, so we'll do some security analysis of WebAssembly as we go, then we'll look into 3 example attack primitives, and finally I'll show you a demo for an exploit on a single WebAssembly platform. Let's start by having an overview of our attack. So the first primitive that we employ is always aiming to obtain a write primitive, like a buffer overflow. Then we direct that to overwrite some sensitive data. And finally, this causes a malicious action in the environment of the WebAssembly binary. So for example, cross-site scripting if it's executed in a browser. In native execution, a couple of mitigations prevent the exploitation to work. And we'll see in a second why they don't apply to WebAssembly. Now, to understand the first part of our attack, we'll have to cover a bit of background on managed versus unmanaged data in WebAssembly. Some data is managed by the VM, so for example scalar variables like this local of integer type, or return addresses. And this is good because they cannot be overwritten by an attacker with a memory vulnerability. A lot of data, however, is not managed by the VM, and that is instead stored in linear memory. So that includes heap allocations, aggregate data like arrays and structs, all data of which an address is ever taken, like function out parameters, and also non-scalar global data, like string literals, for example. And this data could be overwritten by a memory vulnerability. Data with function lifetime is stored in a dedicated portion of linear memory called the unmanaged stack, and we find that this is used by about 1/3 of all functions. Now, how could a buffer overflow on the unmanaged stack be exploited? And for that, we consider this vulnerable program here on the left, which takes some user input and copies that into a fixed size buffer, which is of course unsafe. And then in native execution, we see that an attack is prevented because a stack canary detects the buffer overflow and thus terminates the program and protects return addresses, for example. In WebAssembly, the return address is managed by the VM, which makes it safe from being overwritten, but unfortunately WebAssembly binaries also do away with the stack canaries. So that means on the unmanaged stack, any data that is following the buffer can be freely overwritten, and that includes even data from parent call frames like this other buffer here, for example. Going back to our attack overview, the next step is overwriting some sensitive data. And in order to understand why we can use a stack-based buffer overflow to overwrite heap data, we have to look into WebAssembly's linear memory. Linear memory is essentially a single 32-bit address space available to the WebAssembly program. And that contains all the static, stack, and heap data that I presented before. And because it's a linear memory, it means that every pointer, including the null pointer, is valid. There are no holes in this address space. Linear memory also doesn't feature any page protection flags, so that means there cannot be unmapped pages between the stack and the heap, for example, like in native execution. And it also means that all parts of the memory are always writable. There simply is no way to mark an address as constant or non-writable. And this means that an overflow on the stack, for example, can overwrite into any higher address in linear memory, including heap values, for example. Linear memory also doesn't feature any probabilistic defense. So there's, for example, no ASLR, and the memory layout of stack, heap, and static data is always fully determined from the compiler and the program. Finally, let's think about how overwriting heap data can cause a malicious action in the browser. And for that, let's consider this C++ web application here on the left. And what it does is it first allocates some HTML data on the heap. Then it uses a function from libpng to convert a user-provided image into a PNG file. And then it displays that PNG file by adding HTML to the DOM at runtime. On the right side, you see the layout of linear memory when you compile this application to WebAssembly. Now, in our proof of concept attack, we exploit a memory vulnerability in libpng from 2018. And that first causes a stack overflow and then overwrites data in the heap region, as we've shown before. Since our WebAssembly binary is executing in the browser, as an attacker it makes sense to overwrite the string on the heap with some malicious JavaScript, and that causes cross-site scripting in the browser. In the demo, we see that the WebAssembly application is working as expected when you supply it with a valid image file. So in this case, it converts a PNM image into a PNG file and displays it in the browser. When we choose an attacker-supplied malicious input, however, we see that that causes a stack-to-heap overflow, and that ultimately leads to arbitrary JavaScript execution, so in this case an alert is displayed. Please note that because we don't assume anything besides a standards-compliant browser, this works exactly the same in Safari, Firefox, or Edge. Now, the attack primitives that we've just covered in this demo are of course only a subset of all the attack primitives that we show in the paper. So in particular, we have a couple of primitives along each dimension of our attack, namely obtaining a write primitive, overwriting some sensitive data, and finally performing a malicious action. For the write primitives, we show that not only stack-based buffer overflows are dangerous, but also stack overflows can be exploited, and that a heap overflow can yield a heap metadata corruption, which, given a vulnerable allocator, can give you an arbitrary write primitive. And for overwritten data, we not only target heap data, but also other stack frames and even supposedly constant data. We'll see that in a second. And finally, for the malicious behavior, we not only look into cross-site scripting on the browser platform, but also on remote code execution in Node.js and an arbitrary file write primitive on the WebAssembly systems interface, which is a syscall interface for standalone WebAssembly VMs. As for mitigations, we not only look into stack canaries and unmapped pages, as in this talk, but we also look into safe unlinking, which is often not employed by small WebAssembly allocators for code size reasons. And finally, we also compare WebAssembly's type checking of indirect calls with native control flow integrity techniques. The attack primitives that I've shown you here can be relatively freely combined. So what we've seen in the exploit demo was a stack-based buffer overflow that is not stopped by stack canaries or unmapped pages because they are not present in WebAssembly, that then overrides heap data and then causes a cross-site scripting attack. But we've also provided two other proof-of-concept exploits. The second one starts with a heap metadata corruption, which is not stopped by safe unlinking because the emmalloc allocator doesn't feature it. And then this overwrites data in a parent stack frame. And then we see that because WebAssembly's type checking of indirect calls is not as strict as, for example, native CFI defenses, this can lead to a redirect call and ultimately to the remote code execution. And then the third exploit that we feature in our paper again starts with a stack-based buffer overflow, but this time it targets constant data instead of heap data. So in particular, we overwrite a string literal that is used as a file name later in a C API call. And this gives us an arbitrary file write primitive on a WASI WebAssembly binary. For more details about our attack primitives and the mitigations that we analyzed, please have a look at our full paper. And with that, I would like to conclude this talk and give a short summary of our paper. We look into WebAssembly binary security and compare it to native executables. And we find that because many common mitigations available for native programs are not employed by WebAssembly binaries, that in some cases WebAssembly binaries are less secure than their native counterparts. We realize that a lot of data in a WebAssembly program is not managed by the VM, but instead stored in the unmanaged and completely exposed linear memory. Linear memory itself is much simpler than memory of native programs. So for example, it doesn't have page protections, it doesn't have guard pages, and all memory is always writable. We give a library of attack primitives across 3 dimensions, namely write primitives, overwritten data, and performing a malicious action. And those attack primitives can be relatively freely combined. And we show that our attack primitives are practical by giving 3 example vulnerable applications and end-to-end exploits on 3 different WebAssembly platforms, namely the browser, Node.js, and a standalone WebAssembly VM. And with that, thanks a lot for watching. And if you have any questions, please let us know either via email or we're happy to answer at the USENIX Security 2020 live session. Thanks again and goodbye.